Alright. Oop. That already changed slides for me today. That's nice. So today we're going to go back to orbital mechanics for a little bit. We're going to sprint through it. We're going to cover first half of chapter 2 today, and we're going to cover second half of chapter 2 on Friday. So we're going to be sprinting. Oh, too far. You can do it. I believe in you. Okay, I don't go anywhere. Alright, so to recap from what we covered last time, we were in lecture 3, we went over the problem solution, and we reviewed linearization and the state transition matrix. If you have any questions, just go ahead and post them to the YouTube page, for those of you listening online. So today what we're going to cover is we're going to walk through two-body orbital dynamics, right? So just the two masses acting on each other, Earth and a satellite, in this case for us. We're going to walk through the general properties again real quick, kind of identify those a little more clearly, start talking about planar motion, hop into Kepler's problem, and then finish it off with motion in 3D space and the Greenwich angle, Greenwich time angle. And then what we're going to do is we're going to do the transformation. So we're going to look at orbital elements, transforming them to position and velocity, back again. And we're going to use the state transition matrix and error propagation in there as well. And then I'm going to go walk through the assigned problems. For Kepler's problem through the orbital elements to the position and velocity, we're going to be using the whiteboard today. So I'm just going to switch the camera over to looking at that when we get to that point. So the general properties, all right? So again, this is pretty similar to the slide that we showed first off when we start talking about two-body and orbital mechanics review. We have Newton's law of universal gravitation, right? Gravitational constant times the two masses, and then the direction in which it's acting over r squared, over the magnitude of the distance squared, right? So our assumptions in this case, because we're looking at 2-point bodies or 2-point masses, are that the bodies are also spherically symmetrical, right? And it's a hard assumption, especially when the Earth is so massive, to call it a point mass, but in this case that's what we're doing, right? So the gravitational force also propagates instantaneously. We're ignoring all relativistic effects and anything in that sense. The gravitational constant, again, there it is, the Earth's estimated mass. And so the gravitational parameter, I saw that I had included this symbol last time for the subscript. But, oh, hey there, buddy.
Glad you're doing this.
Yeah. Go ahead and get settled real quick. Orbital mechanics. So we're going to sprint through it, and you guys are going to probably have to come ask me a few times about orbital mechanics, but we'll work through it. So, anyways, so going back to where I was at, the symbol, the subscript for the Earth's mass and the gravitational parameter, that's actually the symbol for Earth, all right? So we have a here, I'll move the camera over. So, symbol for Earth is that circle with a cross. And if I can arrange this correctly. Stop it. Stay. The symbol for Earth is that circle with a cross in the middle of it, right? Well, the symbol for the sun, circle with a dot, right? So, little tidbit. You'll see that come up occasionally, especially in the guys that just want to write shorthand instead of writing out sun, or getting it confused by doing subscripts every time that don't quite, make sense. So they'll start using the astronomical symbols provided. So, moving on. So a relative equation of motion. So this is the M2, or this is our satellite moving with respect to the Earth. That's our differential equation of motion. Remember, we got to that last time. Um, and so that comes into play here because we can actually draw that out of the motion of when we look at Newton's law of universal gravitation. We make the assumption with the gravitational parameter, throw out the other mass, but since we're looking at the relative motion, we take Newton's law of universal gravitation, look at M2, and there are actually some general properties that are important for two-body motion. And we start off with the motion of a two-body center of mass. So the center of mass of two spheres moves in a straight line with a constant velocity. And we can see that when we look at the equation for our center of mass, where our center of mass is. Well, if we plug in the differential equation of motion, right, so we go and look at our R double dot, right, plug it in, add them together, we're actually, because the other term, the other R2 is actually going to be a negative. So we're actually going to see that the acceleration is going to be 0. So then if our acceleration is 0, obviously we're going to have a constant velocity, and it's going to be moving in a straight line, right? So our angular momentum is constant as well. And we can see that, and so therefore our orbital motion is going to be planar, and the orbital plane in which the satellite acts is actually perpendicular to the angular momentum. And we already said this last time as well, but I'm just walking through it again. And you can actually discover this by using the cross product rule. So we take the R cross our differential equation of motion, our relative equation of motion, excuse me, and then using the cross product rule, pull out the differential, and so it's the position crossed with the velocity, right? Well, R crossed over here, remember, so it's constant in R, so it's going to be 0 on that side, on the right-hand side, so we end up with it not changing over time, right? So now we know it's constant. Great, wonderful. Well, the other part of that, guess what else is also constant? Your energy. Your energy per unit mass is constant, and so that's specific to the orbit. So it's particular to the conic section that you're acting about. So whichever orbit you choose, your energy for that particular orbit is going to be constant in the two-body frame of motion. All right. So moving on to planar motion, orbital motion of the mass 2 with respect to m1, we just talked about what that differential equation was, right? So it takes place in the orbital plane, and the orbital plane is orthogonal to that angular momentum. When we're considering it in terms of the inertial, so what I mean here is, let's say we have some inertial frame in the center of the Earth, right? And we're looking at our orbital plane. Well, the way those two interact is that if we had that xy coming out of the Earth, the intersection between the two is actually going to be where our line of nodes is, or where the satellite is going to cross up through and then come back down through. And so the line of nodes connects those 2 points, right? So it's the intersection of that orbital plane with the xy plane in our inertial frame. And then the longitude of the ascending node, or the right angular ascending node, is the angle between the x-axis over to that line of nodes. And we're going to see this in just a second as well, so I won't have to use my hands to explain everything either. And then I is going to be our inclination or our tilt from our z. So for the people that are familiar with rotating to a set of coordinates, right? So if we look at it in rotating to the orbital plane, you're actually going to rotate first using that right angular ascending node or that longitude ascending node, and then you're going to rotate about z, and then you're going to rotate about x, about your new x, in order to tilt that plane, right? So, like I said before, you can see there's our right angular ascending node, or longitude of our ascending node, to our line of nodes, and then we tilt it about the x, about the line of nodes, in order to tilt to our orbital plane. And then you can use your argument of perigee and your true anomaly in order to find the satellite. Well, and the true anomaly is actually what we're going to talk about in just a second, because for your Keplerian orbital elements, remember we talked about it initially, we had our semi-major axis, we had our eccentricity, we had our inclination, we had our argument of perigee, we had our right angular ascending node or our longitude, but we also used the time of periapsis passage, right? Well, the trick with that is that we can actually, a lot of times it's replaced with the mean anomaly. And so that's actually Kepler's problem. And so we're going to walk through that on the whiteboard real quick. Yeah. So let's walk through that on the whiteboard. Stop. Just stay. Okay, cool. There it is. Over here. So let's start off with drawing. Make it a little bit easier on us. So if we have some orbit, right, where we're going to have an elliptical orbit, right, and so we're going to have the Earth at one focus. It's going to be about that orbit. So let's draw a line through this real quick. Okay. So this is our focus, or this is our Earth at this point, right? This is what we're orbiting about, and so we know that our radius of perigee is going to be here. We know our apogee radius is there, right? Semi-major axis is going to be, you can actually just do the apogee radius plus the perigee radius divided by 2 to get your semi-major. But the trick here, what we're really looking at, is if we took the elliptical orbit here, right? And let me make sure I have this right before I do it. If we took the elliptical orbit, let's see if I can get it to stay, and we were to then draw a circle with the same two endpoints. Actually, let me use a different color. Maybe that would be more helpful. Yeah. Well, a circle with the same two endpoints, right? That's the trick, because we have an elliptical orbit, but what we're really doing is our mean anomaly, our eccentric anomaly, and the time of periapsis passage are all going to be related. But the eccentric and the mean, as well as the true anomaly, are all just angles. Okay? So that's a terrible circle, but imagine that the black is a circle about this through those same 2 points for a minute, right? So if we have some satellite here, well, focus, that's our radius to it at that point. Oh, excuse me. It shouldn't be on the circle. Sorry, guys. Yeah, just should be on the ellipse because that's where orbit is. Okay. So if we rotate through this, right, if we were to take the angle here, that's going to be our true anomaly, right? You can use F, you can use V. It's up to you guys, whichever one you want to use, but that's rotating it about. That focus from our perigee is going to be our true anomaly. Well, the trick here is that if we were to, essentially what we're doing is we end up drawing a triangle, and our eccentric anomaly is this angle, right? Okay, and yeah, this is from the center. Sorry, let me do that. Yeah, so if we were to draw it from the center, tracking through to the circle where the satellite currently is, that's going to be our eccentric anomaly. So, make sure there's nothing else that I want to draw out of that. There shouldn't be. No, there's nothing else that I want to draw out of that. Okay. All right. So we're going to end up getting this relationship where because we have this elliptical orbit, I'm not going to do a very good job of explaining it, but long story short, we end up using the mean anomaly because we have an elliptical orbit as opposed to a circular orbit, and so in order to get the right angle, we end up using that mean anomaly as a way of projecting where the satellite actually is going to be. So I just kind of skipped over the math a little bit on that and just said why. So Kepler's equation relates our eccentric anomaly where n is that mean motion, t is the time, and so Tp is the time of perigee passage. And then E is going to be our eccentric anomaly, right? So small e is eccentricity. Yep. So our mean motion is square root of gravitational parameter over our major axis cubed, and that comes actually out of our area, where it's for our, excuse me, not out of our, well, sort of out of our area because we sweep out equal times and equal, or equal areas and equal times, but our period, where it's 2 pi square root a cubed over mu, and so that's where our mean motion comes out of. Anyways, so running through this real quick. Yeah, this gets real fun real fast. Okay, so we can obtain the solution for this through using Newton-Raphson, and what we end up doing is we say that this portion is our mean anomaly. So n t minus Tp is equal to our mean anomaly. Okay, so we end up with E minus E sine E is equal to our mean anomaly. Okay. So root finding method, right? we're going to use G as our descriptor for how good the method is doing. So E minus eccentricity, eccentric anomaly, sine of eccentric anomaly minus mean anomaly, right? And then that'll give us allow us to start working on a predictor through Newton-Raphson, so that iterating would look, or an iterative solution would look where K is the next iteration. So then we would use this for our Newton-Raphson. Right. Okay, great. So that's how we would. There are a lot of relations in the book where it describes, it uses basically some quadrant checks, and there are there's quite a few papers devoted to actually discovering the best way to do Kepler's problem, because Kepler's problem is determined on eccentric anomaly, right? And so back in the day, there was, especially with limited computational space, there were quite a few papers on how to do this efficiently. Doesn't mean that we haven't stopped trying to think about how to do this efficiently. It just means that we also tend to have a little bit more space, and so we can be a little more careless in how we choose to attack this problem. And so this will end up giving you that sixth orbital element as opposed to your time and perigee passage, right? So it's another angle, which is almost infinitely more useful, and then you can relate that back to your true anomaly later. If you want, let me see if, yeah, okay. So, moving on, let's see, what was our next one? We did planar motion, basic coordinate, the orbital elements and the position and velocity. Okay, great. This is the fun one today for writing. So, let's assume that we've determined we're going to go from position and velocity to the orbital elements right now. So let's assume that we've already predetermined the state vector. So that means that we know our, so x, I, j, and then x dot, y dot, z dot. Okay, let's assume we took some observation and we know these at some time tk, right? So, the first step that we're going to do is we want to find our orbital elements, right? Well, what do we know right off the top of our Well, we have position and velocity. If we cross them, we're going to get our angular momentum, right? Okay, so we can just do that one first. R cross R dot. Great, found it. So our next step, we can go back and we can find the energy per unit mass, right? So we can find our specific energy for this particular orbit. We have the initial velocity, or the magnitude of the initial velocity squared divided by 2, right? We can also just write that as r dot dotted with itself over 2 minus, it's going to be mu over the magnitude of r, or our position, at that time. Let's see. Okay, great. So we've got our angular momentum. We've got our specific energy. Well, when we have our specific energy, we can find out our semi-major axis pretty easily. Our semi-major axis out of our specific energy is simply going to be, actually let's write this in terms of semi-major axis first. Ta-da! There's our semi-major axis. Okay. Our eccentricity is also related through our angular momentum and through our semi-major axis. Excuse me. And as well as our specific energy. Our eccentricity is where we get our specific energy and our angular momentum. So we have our eccentricity, 1 plus h squared divided by the gravitational parameter. And make it to be clear that angular momentum is a magnitude squared. So that would, I could also just write, instead of angular momentum squared, I could also just write the vector of angular momentum dotted with itself. And that's, any vector dotted with itself is equal to that vector squared, or the magnitude of that vector squared. Okay, so I could write that there. And then we're square rooting all of this in order to find the eccentricity. Fair enough? Okay. Well, remember I brought up semi-lattice rectum last time. This is where it comes into play, because then we're going to find our true anomaly out of it. So you guys have everything on here? Okay. As far as semi-lattice rectum is going to be P, not to confuse that with range. I'm so used to writing rho at this point. P is equal to h squared, so our angular momentum squared, over, I believe it's mu, but let me double check. Yes, it is mu, our gravitational parameter. Okay, great, wonderful. That's our semi-lattice rectum. So our true anomaly, we can find, and we're going to have to use a quadrant check at this point. All right, I'm going to use V for us. We can use V, we can use F. Let's make a decision now. Which one are we going to use, V or F?
I like V.
You like V? Okay. Okay, cool. Sounds good. Just so that I'm consistent with you guys. 1 over, so that's our initial position. So that would be here. Let's just do it this way. A little more complicated, but there we go. Sound good? Because all that's going to be is the magnitude of the vector squared, and then if we take the square root of it, then it's just our initial vector anyways. Right? And then times our eccentricity. And then our semi-lattice rectum comes into play. Geez, I keep writing a row. P minus, same thing we just did, underneath, down in square root so that we have the magnitude. Ta-da! So that's our cosine. Our sine is going to be semi-lattice rectum over magnitude of the angular momentum, eccentricity, and then R dotted with R over the magnitude. Okay. So we have both, so we can do a quadrant check, make sure that we have it correct. The next one that we're going to do is our argument of perigee plus our true anomaly. And that looks like we're going to use individual components at this point. So this x is from the position vector. Cosine of the longitude of the ascending node plus y over magnitude of r again, and then sine of the longitude of the ascending node, correct, yep. And then sine of our argument of perigee plus our true anomaly. We're going to need our z over magnitude of the position vector multiplied by sine of the inclination. And so your inclination, you can actually, that's why we do angular momentum first, because you can find your inclination from, it's the angle between your angular momentum and your z, right? So if we know where z is, quote unquote, then it's just the angle between the two. So as long as you know your frame of reference that we just gave those initial coordinates in, right, you should know your inclination at that point if you're able to figure out your angular momentum. So now that we've given this in terms of our true anomaly and in terms of our argument of perigee plus our true anomaly, you should be able to figure out your argument of perigee or your argument of perifocus from little omega is equal to plus and minus. Right? Oh, sorry, not F. We're using V. Ta-da. Right? I would hope that you guys would be able to do that after finding that angle. Right? So, anyways. And all right, remember our eccentric anomaly. We're going to use our eccentric anomaly and our mean anomaly real quick. So remember mean anomaly, Kepler's problem, and it's equal to E minus the eccentricity sine of the eccentric anomaly. Our eccentric anomaly can be found using cosine and sine. So that looks like our magnitude of R A plus eccentricity. And then this is the semi-minor. B is actually the semi-minor axis. You can actually get around that if you want to and use a different parameter, but for now, just make it easy on myself, we're going to use the semi-minor axis. Then remember, for our mean anomaly is related through the mean motion to, our mean anomaly actually is the mean motion times the current time minus the time of perigee passage or perifocus passage, so that we can shift things around here. We get our time minus the mean anomaly over mean motion. So, yeah, so we moved all the way through, got all of our orbital elements done. What time are we at, guys? What?
49.
49. Okay. We will pick up with the state transition and error propagation next time, but let's run through the problems real fast. Stay. Okay. Let's run through the problems real fast. Hey, predict the orbit. Great. Wonderful. Okay. So I'm giving you 3 problems involving orbital motion to make sure that you guys understand what's going on. So these are intended to help you and test your knowledge. Feel free to come ask me questions or post questions on the YouTube page, however you want to do it. And these problems should be done by Monday. Okay.
What do you want that turned in? Like you want it right out?
No, electronically is fine, but for you guys, just shoot me an email. And then for anybody else that is doing this, this is kind of follow along at their own pace. So they can email it to me by, they should have that once they get on the mailing list, my email. Or they can post a link to it on their website. Well, whatever works for them. But for you guys, I'd like you guys to email it to me. Just email that memo. And yeah, so should be done by Monday. First problem. I give you the position and velocity of a satellite. The position and velocity are in a non-rotating geocentric system. Determine the 6 orbital elements, including mean anomaly, assuming that the initial state is given and the two-body is given and two-body motion. So in other words, that the position and velocity I give you is at time 0. Predict the position and velocity at t equals 3,000 seconds. Right? Tell me what the flight path angle at that time is. And then you're going to, for the third part of this, you're going to determine the latitude and longitude of the sub-satellite point. So essentially the point on the Earth, right? For time equals 3,000 seconds if the angle for the Greenwich angle at time equals 0 is 0. Assume the z-axis of that non-rotating system is coincident with the z-axis of the rotating system. Because you're going to need an Earth-fixed rotating system in order to find that longitude, latitude. That's what's going on there. So your second problem, there's a payload that goes off the Shuttle Discovery in 1997. Has a GPS receiver on board. You get those 2 printouts from an Earth-centered, Earth-fixed coordinate system. And these are your position, by the way, in GPS, or from the GPS. So demonstrate that the node location is not fixed in space. So in other words, it's perturbed. And determine an approximate rate of node change from these positions. And then you're going to compare it with that equation provided to you, which is also in the textbook. I believe it's 2.3.31 is the equation. And then you're going to determine the inclination during the first 3-second interval and the last 3-second interval of those position coordinates given to you. And remember, so in this case, the position vectors determined by GPS are influenced at the 100-meter level by selective ability, but the error is not going to significantly affect this problem. And finally, GLONASS. GLONASS is Russia's answer for American GPS. They have 26 satellites in orbit, 24 of which are currently operating. And we're going to assume we're going to use a satellite in a GLONASS-like orbit. Assuming that the satellite's influenced by J2 only, you're going to develop the equations of motion. And then you're going to integrate those equations of motion for 1 day. During the integration, you're going to compute the Jacobi constant and the z component of the angular momentum. You're going to plot the 6 orbital elements as a function of time. You're going to identify, and so those figures I will show you those figures later, but because this is an online course, I'm not sure about whether or not I can actually show those figures from the textbook. So like these problems are similar to ones in the textbook, In some cases using some of the same numbers, but I wanted it to be a little bit different so that I wasn't taking it directly from the textbook because I'm not sure of how much I can actually put online. So for those figures, I'll show you those right after class. And then you're going to compare the node rate again. And you're also going to compare the amplitude of the semi-major axis periodic term as well, because your semi-major axis is going to be changing as well due to that J2 perturbation, right? And these are your initial values, but you're also going to plot the ground track and tell me if the ground track repeats after 1 day. But those are your initial values for that satellite. Fair enough? It's a lot?
Yeah.
Okay. All right. Good deal. All right. That's all I got for today. We'll pick up again. I'll pick up again on Friday.